Hello and welcome to the Ways of Math. I'm your host, Dan the Math Man, and today we're going to continue our series on Introduction to Basic Probability. This is the second part of this multi-part series. Before we get started, please be sure to subscribe to the channel to be notified of future videos, and also please leave any comments or suggestions that you have in the comment and suggestion box below. In today's video, this is part 2. We're going to discuss the law of large numbers and the probability complement. So what is the complement of a probability? Okay, let's get started. So in this video, we're going to discuss the law of large numbers and its importance to probability, right? Because this is actually a very important concept in probability. So we want to describe why is it important and what does it really mean. Also, we're going to talk about the complement of a probability, right? Known as the probability complement. And of course, we're going to give some examples again to help kind of explain these and kind of motivate the concept and drive the concept forward. Okay, so with the law of large numbers, okay, this is a really important statement about the nature of probability, right? So this kind of generalizes really how we think about probability and how we look at probability, and it also kind of sets up, what is it that we're really doing with probability in terms of understanding and what does it do for us and how do we interpret it. So it kind of generally states that probability statements apply to a large number of trials, not to individual trials. It consists of the relative frequency over the long term, or it is the relative frequency over the long term that can be accurately predicted, while individual events and precise totals cannot be, right? So what we're saying here is probability kind of gives us an idea or a gauge of what will happen over a long number of trials. So if we were to, so even with theoretical probability, okay, the theoretical probability is simply stating that if we were to perform the experiment a large number of times, then the relative frequency of occurrence kind of coincides with what the theoretical probability tells us. So the empirical probability gets closer and closer to the theoretical probability, okay, over the long term. So it's in fact because of this reason, right, this law of large numbers, that things like casinos and lotteries can operate, right? So even though they give out money to individual winners and things like that, so they lose money over kind of a short term, over the long term, and this is why they control the probability. So if you actually look at the probabilities of winning at a casino or winning at a lottery or things like that, the probabilities are fixed so that they have the advantage. So over the long term, they will ultimately gain a profit. So even though they lose money on individual outcomes, long term, they actually are winning and they gain profit, okay? And so to kind of better exemplify this, right, and see this happening, let's consider the following example, right? So suppose we have a die or a coin and we're going to flip it, right? So in the first column, we see the number of times that we flipped it. The second column, this is what we expect to happen if we're flipping a fair coin. This third column is the number of times we actually observed a head being face up over the, so this is the actual frequency of occurrence, the observed value of the number of heads that we saw face up. And then, of course, we compute the probability, the empirical probability or the relative frequency of actually obtaining heads, right? So, right, with 10 tosses, again, we're assuming we're dealing with a fair coin, so we assume that roughly half of the results will be heads and half will be tails. So that's what we expect. Now, in this case, we flipped the coin 10 times and we actually got 6 heads. So the relative frequency in that case is 6/10 or 0.6. Now, we took the same coin, we flipped it 100 times. And again, we expect to kind of see 50 heads is what we expect to see. But we actually observed 52. And so we get this probability of 52 over 100, or approximately 0.52, or exactly 0.52. Okay. Now, when we flip it 1,000 times, we expect to see 500 heads. We actually observed 507, giving us a probability of 0.507. Now, if we've rolled it 50,000 or flipped it 50,000 times, we expect, again, half of those, 25,000, to be the number of occurrences of heads. We actually see 24,975, which gives us a relative frequency of 0.4995. Now, we've flipped the coin 1 million times. Again, the expected number of heads to be half, it's 500,000. The number of actually observed number of heads was 49,947, giving us a relative frequency of 0.499947, right? So what does this mean? Notice the values of these relative frequencies. The more tosses, the longer the experiment runs, we see these values are getting closer and closer to exactly half, 0.5, right? That's kind of the expected relative frequency that we want to see, right? So even though individual short-term experiments have different relative frequencies, the long term, as we do this experiment over and over and over again, we get closer and closer to the expected number, right? I mean, we're still off. In this case, we're off by 53 flips. There are 53 flips that should have been heads that ended up not being heads, okay? But notice that this number is a lot closer to this number than 52 was to 50 or 507 was to 500, okay? So again, short-term trials might vary from the predicted values. However, as the number of trials increase, that variability kind of levels off, and the actual values get closer and closer to the long-term predicted values. So the theoretical probability is the long-term predicted value, while the relative frequency of the empirical is kind of the short-term observations of these values. Okay? Now, you might ask, and it seems logical to ask, well, haven't we been using probability to predict individual outcomes? And doesn't that contradict the law of large numbers? Well, in short, the answer is no. Remember the wording. When we use probability correctly, we are predicting the likelihood of an outcome, not the actual outcome, right? The likelihood of flipping heads on a fair coin is 1/2. That doesn't say that on any given flip we're going to get heads or tails, right? It doesn't give us a means of predicting that the next one will be heads or the next one will be tails. It only gives us a gauge for what the long term will be. So in fact, if we properly understand what the probability of 1/2 means, we're really saying that over the course of the long term, if we divide it out, approximately 1 out of every 2 flips will result in heads up over the long term, not in the short term, right? We might have 4 flips in a row that are all tails. That doesn't change the fact that the probability of getting heads is 1 out of 2, or 1/2, okay? So the law of large numbers and probability in general doesn't say anything about every small set of trials, and it doesn't guarantee exactly what the results will be. What we are in fact observing, the law of large numbers in every probability that we compute. Okay, again, the law of large numbers is essentially saying if we perform an experiment a large enough number of times, then the relative frequency, the value of the relative frequency, gets closer and closer and approaches the theoretical probability. Okay, hopefully that makes sense for you. It's an incredibly important concept. Now, we'll move on to another really important idea, and this is the concept of probability complement, okay? Or the complement of a probability, right? So again, we'll kind of start with this, with a definition. So the complement of a probability is the probability of the complement of an event, okay? I'm going to say that one more time. So the complement of a probability is the probability of the complement of an event. Now, for those of you who have taken a little bit of set theory or possibly watched my series on Introduction to Sets, okay, you should be aware of or familiar with the concept of the complement of a set, okay? We'll just kind of explain it, but this series does not rely heavily on set theory, so we'll explain what that means. So, for some event E, we write the complement as E with this little c, so this E complement. Okay, now what does that mean? So the complement of an event is simply all other outcomes that are not in the event. Remember that an event is a set of outcomes. So the complement of the event is all the outcomes that are not in the event. So it's all the other outcomes. Okay? So this idea of the complement of a probability, right, is, so for if we have any probability of E, right, P of E, we express the complement of the probability as the probability of the complement of the event. Okay? Now this is kind of formal set notation. We don't have to necessarily use that formal notation. We can also express in the complement in words, and we use the word usually we use the word not. So we can say equivalently to the probability of the complement of E as being the probability of it not being E. So probability that the outcomes are not in the event. Okay, so now notice for any event, we only have two possibilities. Either the event happens, right? One of the outcomes within the event happens, or they don't, right? So the event doesn't happen, right? That's the only two possibilities. So therefore, the probability of the event E plus the probability of the complement of E are the only possibilities for that event. Okay, so from this, we can infer a formula, right? Remember that all distinct possibilities, the probabilities of these, must equal 1, right? Because something has to happen. So either the event happens or it doesn't happen. So we can think of the probability of the event plus the probability of the complement of the event must always equal 1. Because again, this is the event E is the set of all outcomes, right, in the event, and the complement of E is the set of all other outcomes that are not in the event. Okay? So this is going to be the probability of either these outcomes happening or all the other outcomes happening. Okay? Now, usually we use the formula in this form, which is to say that the probability of the complement of an event is equal to 1 minus the probability of the event. Don't worry, we have an example in store for how to use this. Okay, so let's consider a fair six-sided die. Okay, so we want to determine the probability of a 4 being rolled, a 4 not being rolled. First, we'll do this directly without considering the probability complement. And then we want to find the probability that a 4 is not rolled, and this time we're going to use the probability complement. Okay, so let's take a look at the solution for this. So for part 1, again, recall that for a six-sided die, there are 6 distinct sides. Okay, each of them equally likely to be rolled because this is a fair die. So the probability of rolling a 4 is going to equal the number of 4s that are on the side divided by the total number of sides. Well, there's only one 4 on a six-sided die, and there's 6 total sides. So then the probability of rolling a 4 is 1/6. Okay? Now, this time we're going to consider finding the probability of not rolling a 4, and we're going to look at it just directly. We're not going to consider the complement, and let's see what we get. So, in fact, if we're not going to roll a 4, so if we're trying to find the probability of not rolling a 4, then it's really the same thing as saying rolling something other than a 4, right? Well, the other possibilities are 1, 2, 3, 5, or 6, right? So when we ask the probability of not rolling a 4, that's equivalent to saying the probability of rolling a 1, or a 2, or a 3, or a 5, or a 6. Okay? Now again, each one of these outcomes are equally likely to be obtained, right? Equally likely to happen because it's a fair die. So the probability of not rolling a 4 is equal to the number of non-4s, so the number of sides that don't have a 4, right? There's 5 of them, right? 1, 2, 3, 5, and 6, divided by the total number of sides, which is 6. So we get the result is 5/6. Now we're going to repeat this same computation, but this time we're going to use the probability complement. So this time we are going to reorganize the event of not rolling a 4. This is, in fact, like we discussed earlier, the complement to the event of rolling a 4. So therefore, we can use the probability complement formula. So the probability of not rolling a 4 right? This is the complement of rolling a 4, is equal to 1 minus the probability of rolling a 4. Well, we already obtained that. The probability of rolling a 4 was 1/6. That was the first step in this example. So 1 minus 1/6, simplifying that, we get 5/6. So we see that we obtain the same results that we did previously. Now notice, if we had more outcomes to consider, this might be a much easier probability to compute, right? So, I mean, in this case, we only had 6 possible outcomes, but suppose it was a little more complicated. We were dealing with, say, a 52-card deck, and we wanted to know, like, what's the probability of not getting a black card or a face card, right? That might be a lot harder to figure out versus what's the probability of getting a black card and a face card, right? That's the complement of not getting a black card or a face card, okay? And again, we'll do more examples of this later, but the motivation here is that sometimes it's much easier to consider the probability complement, and therefore computationally easier to use the probability complement than it is to compute it directly. So to kind of summarize what we've done in this video. So we discussed the law of large numbers, and it tells us that probability is best suited for determining long-term outcomes, right? So we can accurately predict long-term outcomes, okay, using probability, right? And this is because of the law of large numbers. However, specific individual outcomes and specific totals cannot be accurately predicted. That's not what we use probability for, right? On any given flip, we might say or the coin flip experiment. Probability doesn't tell us anything about what the 67th flip is going to be. It doesn't give us anything about whether that's going to be, it's more likely to be a tail or more likely to be a head. It doesn't give us anything like that. But it does say that over the long term, the likelihood of the total number of heads observed or the likelihood of the total number of tails observed is 1/2. Okay, and that's the ratio of the observed frequency over the total number of experiments that were performed. Okay, it also, again, doesn't give us specific totals, right? We might run it 10,000 times, 100,000 times, 1,000,000 times. It doesn't say we're going to obtain exactly 552,000 heads out of running it 600,000 times or 100,000 times or 1,000,000 times or whatever you can come up with, right? It simply predicts the likelihood of the individual outcome, and it gives the long-term probability of those outcomes occurring. It doesn't determine what the individual outcome is, just the likelihood of an individual outcome. Okay, then we also talked about the complementary probability, so the probability complement, and we kind of recall the information that the sum of a probability and its complement is always 1, right? Because either the event happens or it does not happen. So therefore, if we add these two probabilities together, we must get 1 because one of those two things must happen. Either it happens or it doesn't happen. Now, it's not always easy to define the complement on an event, so we can solve for its probability by knowing the probability of the event itself and subtracting it from 1. So instead of determining and defining specifically what the complement of an event is, if we just know the probability of that event, we can compute the probability of the complement by using this formula, right? Again, this is the set theory way of notating this. The probability of an event complement is equal to 1 minus the probability of the event. But again, we can say that, in words, the probability that we don't, or that event does not occur. So probability that the event does not occur is equal to 1 minus the probability that the event does occur. Okay. I hope you enjoyed this video, and I hope this explained the concepts as clearly as possible. As always, I appreciate you watching, so thank you so much. Please be sure to subscribe and leave any comments or suggestions in the comment box below. And as always, have a wonderful math-filled day.